Hello everybody. Today we will discuss problems from the first tour of US Olympiad year 2008 F equal MA. There are as usual 25 problems for which you will get 75 minutes and you need to solve as much as possible problems. So again, we need to emphasize that first you have to try to solve easiest problems, and after that, when you solve easy problem, go ahead and try to solve a more difficult problem. So first problem: a bird flying in a straight line, initially at 10 meters per second. Uniformly increases its speed to 18 meters per second, while covering a distance of 40 meters. What is the magnitude of the acceleration of the bird? Solution. This is typical kinematic problem to use regular kinematic equations for motion with acceleration, with constant acceleration. There are 4 equations which we use for such kinematic problems. First 3 they include time, and equation number 4 it's without time, which is connecting initial and final speed, distance, and acceleration. And this equation in form of acceleration, to find acceleration, looks like this. Here we have such notation. We have final speed v2 equal 18 meters per second, initial speed is 10 meters per second, and the distance is 40 meters. And this is our kinematic relation between all these things. So this is how to calculate what is the acceleration. Now we can input numbers, and this is a solution. We have finally 2.8 meters per second square. Of course, this is D answer. Problem number 2. A cockroach is crawling along the walls inside the cubicle room that has an edge length of 3 meters. If the cockroach starts from the back lower left hand corner of the cube and finishes at the front upper right hand corner, what is the magnitude of the displacement of the cockroach? Solution. This is a pure geometrical problem. We have to find total displacement, not total path of travel, not total distance. So we just need to find what is the straight line length between initial position and final position. If initial position is 0, 0, 0 in 3D, so the final position is x equal 3, y equal 3, and z equal 3. So which give us so we have d square equal x square plus y square plus z square. It means that d equal 3 root over 2 over 3. So the answer is 3 root 3, which is C, correct answer. Problem number 3. The position versus time graph for an object moving in a straight line is shown here. What is the instantaneous velocity at time t equal 2 seconds? We know that instantaneous velocity measured the tangent line in graph position versus time. But here we have this graph exactly straight line. So it means that velocity will be the same in any point. So we can just use next equation to find what is the slope. So here we can count slope from 0.2 seconds, and here we have displacement is 0, and in time 0 seconds we have displacement 4 meters. So the formula is dx over dt equal 0 minus 4 over 2 seconds, which is negative 2. So this is the answer. Correct answer is negative 2 meters per second. Problem number 4. The information below is for the next two problems. Shown below is the velocity versus time graph for a toy car moving along a straight line. What is the maximum displacement from start for the toy car? As we can see on this graph, when we have graph velocity versus time, we can find what is total displacement using calculation of area under the graph. If velocity is positive, area is positive. If velocity is negative, it means that area is negative. So if we see, if we want to find where is the maximum displacement, we need to move till velocity is positive. So we will move till 2.5 seconds. And we have to find what is the area under this graph from 0 to 2.5 seconds. Let's count it. From 0 to 1, that will be 2 and 4. That's half. Average of this is 3. So it's total 3 here. From 1 to 1.5, we have 0.5 multiplied by 4, which is 2. So here we have 3 and here we have 2. Total is 5. And last is triangle from 1.5 till 2.5. So base is 1 and the height is 4. So total area for this triangle is 2. So total is 3 plus 2 plus 2, which is 7. Correct answer is D, 7 meters. Problem 5. Which of the following acceleration versus time graphs most closely represents the acceleration of the toy car? Let's check this graph. Velocity versus time. Acceleration is a slope. So it means that from 0 to 1 seconds we have positive acceleration 2. From 1 to 1.5 we have 0 acceleration. And from 1.5 till 3 we have negative acceleration, negative 4. So here we have positive 2, 0, negative 4. Let's check all these 5 graphs. Graph A. We have positive here from 0 to 1. We have 0 from 1 to 1.5. But here we have positive. So it's no good. We're supposed to have a negative. So A is no good. B. We have positive from 0 to 1 and 0 from 1 to 1.5. And we have negative there. But the difference is that here we have positive 2 and negative 4. And here we have positive, but negative is twice less than positive. So it's no good. It's supposed to be negative twice greater by absolute value. Let's check C. We have first thing positive, after that we have 0, and after that we have negative, and this negative is twice greater than this positive. So that's a good solution. Probably C is a good solution. Let's check two others. D, we have good from 0 to 1, that's positive. We have 0 from 1 to 1.5, and we have from 1.5 to 2.5. It's again good, but last from 0.5 till 3 we have positive, but it's supposed to be still negative, so it's no good. And E is no good because from 1 to 1.5 it's not 0, which is no good. So that's it. C is correct answer. Problem number 6. A cannon fires projectiles on a flat range at a fixed speed but with a variable angle. The maximum range of the cannon is big L. What is the range of the cannon when it fires at angle pi/6 above the horizontal? Ignore I resistance. Solution. We know that range for cannon equal like this: D equal V square over G multiplied by double angle theta. Maximum range we have when theta equal pi/4, so it means that sine equal 1. And what happens when we have angle pi/6? In that case, we have D equal V square over G multiplied by sine pi/3, which is √3/2. So it means that total solution will be √3/2 big L, which is A, correct answer. Problem number 4. The information below is for the next two problems. Shown below is the velocity versus time graph for a toy car moving along a straight line. What is the maximum displacement from start for the toy car? As we can see on this graph, when we have graph velocity versus time, we can find what is total displacement using calculation of area under the graph. If velocity is positive, area is positive. If velocity is negative, it means that area is negative. So if we see, if we want to find where is the maximum displacement, we need to move till velocity is positive. So we will move till 2.5 seconds. And we have to find what is the area under this graph from 0 to 2.5 seconds. Let's count it. From 0 to 1, that will be 2 and 4. That's half. Average of this is 3. So it's total 3 here. From 1 to 1.5, we have 0.5 multiplied by 4, which is 2. So here we have 3 and here we have 2. Total is 5. And last is triangle from 1.5 till 2.5. So base is 1 and the height is 4. So total area for this triangle is 2. So total is 3 plus 2 plus 2, which is 7. Correct answer is D, 7 meters. Problem 5. Which of the following acceleration versus time graphs most closely represents the acceleration of the toy car. Let's check this graph, velocity versus time. Acceleration is a slope, so it means that from 0 to 1 seconds we have positive acceleration 2. From 1 to 1.5 we have a 0 acceleration, and from 1.5 till 3 we have negative acceleration, -4. So here we have +2, 0, -4. Let's check all these 5 graphs. Graph A, we have positive here from 0 to 1, we have 0 from 1 to 1.5, but here we have positive, so it's no good. We're supposed to have a negative, so A is no good. B, we have positive from 0 to 1 and 0 from 1 to 1.5, and we have negative there, but the difference is that here we have +2 and -4, and here we have positive, but negative is twice less than positive, so it's no good. It's supposed to be negative twice greater by absolute value. Let's check C. We have first thing positive, after that we have 0, and after that we have negative, and this negative is twice greater than this positive. So that's a good solution. Probably C is a good solution. Let's check 2 others. D, we have good from 0 to 1, that's positive. We have 0 from 1 to 1.5, and we have from 1.5 to 2.5. It's again good, but last from 0.5 till 3 we have positive, but it's supposed to be still negative, so it's no good. And E is no good because from 1 to 1.5 it's not 0, which is no good. So that's it. C is correct answer. Problem number 6. A cannon fires projectiles on a flat range at a fixed speed but with a variable angle. The maximum range of the cannon is big L. What is the range of the cannon when it fires at angle pi/6 above the horizontal? Ignore I resistance. Solution. We know that the range for cannon equal like this: d equal v square over g multiplied by double angle theta. Maximum range we have when theta equal pi/4, so it means that sine equal 1. And what happens when we have angle pi/6? In that case, we have d equal v square over g multiplied by sine pi/3, which is √3/2. So it means that total solution will be √3/2 big L, which is A, correct answer. Problem number 10. The following information applies to the next 2 problems. An experiment consists of pulling a heavy wooden block across a level surface with a spring force meter. The constant force for each try is recorded, as is the acceleration of the block. The data are shown below. Which is the best value for the mass of the block? So first of all, we can write here the equation for motion. This is our equation. mass multiplied by acceleration equal force of the spring minus force of friction, which is mu mg. If we look at this equation and look at this representing data, we can see that force is a function of acceleration, and according to this equation it must be straight line. And we can draw a picture. From this picture we can see that mass could be defined as a slope of this graph. So delta F divided by delta A. And the best way to choose this delta is to take furthest points, like this one and this one, and this one and this one. So we can write this immediately. We choose points 5.05 minus 3.05 divided by 0.495 minus 0.95, 0.9. So this is our answer. We have mass equal 5 kilogram, which is a B answer. Problem number 11. We have the same setup as for previous problem, number 10, but the question is this. Which is the best value of the coefficient of friction between the block and the surface? Again, to solve this problem, we can use this equation, m equal F minus mu mg. And now we already counted what is the mass. It's 5 kilograms. So we can use all data which we already have, and this is our calculations. So here we use force 5.05 and acceleration 0.495. Put it in this formula, and finally we found that mu equal 0.05. That's answer A. Problem number 12. A uniform disk rotates at a fixed angular velocity on an axis through its center normal to the plane of the disk and has kinetic energy E. If the same disk rotates at the same angular velocity about an axis on the edge of the disk, still normal to the plane of the disk, what is its kinetic energy? So first here let's draw the picture. If our disk rotates around the center, point O, we have a moment of inertia at this disk equal to 0, which is 1/2 mr square. This is formula for uniform disk. But from other hand, if this disk rotates around a point on some kind of distance d from the center of this disk, center of mass of this disk, we use a so-called parallel axis theorem, which states that moment of inertia equal to moment of inertia around center of mass plus md square, where d is distance between center of mass and the point of rotation. In our case, distance is equal exactly radius, and it means that we just triple moment of inertia. And last point, kinetic energy for rotation. The formula is, we see that kinetic energy proportional to moment of inertia. If we triple moment of inertia and leave the same angular velocity, we will triple our energy. It means that the answer is D, 3E. Problem number 16. A massless spring with a spring constant K is vertically mounted so that the bottom end is firmly attached to the ground and the top end free. A ball with mass M falls vertically down on the top end of the spring, becoming attached, so that the ball oscillates vertically on the spring. What equation describes the acceleration of the ball when it is at height y above the original position of the top end of the spring? Let down be negative and neglect air resistance. G is the magnitude of the acceleration of free fall. So first let's draw the picture for this process. Initially a spring is in neutral position, and after mass is attached to the platform, it starts to oscillate in the position y above the neutral. We can figure which forces acting on this mass. So first force is from spring. It's equal to negative ky, because y is positive, and it's a regular formula for force with a Hookean spring. And other force is mg, which is going to negative 2. So we can write this equation. So that's the equation for motion for this ball. And now we can find what is the acceleration. This is the final equation for acceleration. So we can see that it's exactly E, correct answer. Problem 17. A mass M is resting at equilibrium, suspended from a vertical spring of natural length L and the spring constant K, inside a box as shown. The box begins accelerating upward with the acceleration A. How much closer does the equilibrium position of the mass move to the bottom of the box? So first of all, we can write equation for how to find what is the displacement of mass from initial equilibrium to equilibrium with the mass attached to the spring. mg equal negative kx1. If we start to move this box upward with acceleration A, its best way to do is to move to the new frame of reference, which is going with acceleration A upward. In this frame we have additional frictional force, like additional force of gravity acting on all bodies. So it means that we can replace gravity acceleration G with the gravity acceleration G plus A. In that case, a new equation for the equilibrium position will be this one. So now let's subtract from this equation which describe what is the displacement of our new equilibrium position. That's x2 minus x1. x2 minus x1 equal negative ma over k. So, and the question was what is the new position down to the bottom. So it means that answer is ma over k, which is E. Problem number 18. A uniform circular ring of radius big R is fixed in a place. A particle is placed on the axis of the ring at a distance much greater than R and allow it to fall toward the ring under the influence of the ring's gravity. The particle achieves a maximum speed v. The ring is replaced with one of the same linear mass density but radius 2r, and the experiment is repeated. what is the new maximum speed of the particle. So first of all, if we are very far from ring, we can make potential energy equal 0 in the infinity. And now let's calculate what is the potential energy in the center of the ring when particle achieved it. That's obviously be this expression: potential energy equal negative g, mass of the ring multiplied by mass of the body and divided by radius, because all mass of the ring has a distance r from the center of this ring. It means that this particle will get kinetic energy equal to difference of potential energy, K equal positive expression for potential energy. Now let's see what happens if we have double ring with the same linear density and repeat this experiment. If we double linear density, it means that total mass of the ring will double, but the distance from the center of the ring will double too. So it means that for expression for potential energy will be like this: we double mass, we double radius, they will cancel each other, and potential energy will be the same. It means that particle will get the same kinetic energy, which means that speed, maximum speed will be the same. So correct answer is C. Problem 19. A car has an engine which delivers a constant power. It accelerates from rest at time t equals 0, and at time t equal t0 its acceleration is a0. What is its acceleration at time equal to t0? Ignore any loss due to friction. So first of all, let's write the expression for power. We know that power equal to applied force multiplied by speed, which means that for a regular car that will be mass multiplied by acceleration and by speed. From other hand, we know that if we don't lose any power, all power going to kinetic energy, because we have constant power, our kinetic energy increases linearly. So this is the expression for kinetic energy. This expression is good for time equal t0. If we have time equal to t0, we have to double our kinetic energy, which is this one. And from here we can immediately say speed equal root 2 v0. This is how our speed increases with time. And now, if we look at this expression, if we increase v in root 2 times, it means that our acceleration will decrease on the same value. So finally we have acceleration a equal 1 over root 2 a0. This is the B answer. Problem number 20. The Young's modulus E of a material measures how stiff it is. The larger the value of E, the more stiff the material. Consider a solid rectangular steel beam which is anchored horizontally to the wall at one end and allowed to deflect under its own weight. The beam has a length L, vertical thickness h, width w, mass density ρ, and the Young's modulus E. The acceleration due to gravity is g. What is the distance through which the other end moves? Beam sagging. Hint: You are expected to solve this problem by eliminating implausible answers. All of the choices are dimensionally correct. Solution. Usually such problems in US Olympia, they are connected to dimensional analysis, but here they already told that dimensions are all correct, so we just need to make quality analysis, which parameters has what kind of influence on this deflecting. Let's start with this table. We will check for each parameter how it will affect this deflection, and exclude what can we exclude. So first of all, Young modulus, it's how stiff it is. It means that how difficult under the gravity, for example, to compress or to stretch our beam. So let's see, first A. If we increase E, this expression decreased, so that's possibility. We can mention it here. A. Next one is B. Same thing, we increase E, deflection decreasing, so B is correct. C is not correct because it's not including E, but it must, so C is no good. D. Same thing, D is good because for same reason we will increase E, deflection decreasing. D and E no good, we increase E and deflection increasing, which is not correct. Let's talk about L, parameter L. If we enlarge parameter L, for sure this deflection will increase, so this is good for choice A. For choice B, for choice C, for choice D, and for choice E. Oh, I'm sorry, it's not including in B, so B is no good. Let's talk about parameter H, height. If we increase H, we increase vertical thickness. It means that this deflection will decrease. A is no good. B is no good. C is no good. Only D and E good. D and E. W is not included, and it's obviously has no influence. And rho G, let's check rho G. Rho G, if we increase rho and G, deflection will increase, so it means that A is good, B is good, C no good, D good, and E is not good. So analyzing all these answers, we can see that only D is correct. It's included in all of them, so D is correct answer. Problem number 21. Consider a particle at rest which may decay into 2 daughter particles or into 3 daughter particles. Which of the following is true in the two-body case, but false in the three-body case. There are no external forces. A. Velocity vectors of the dotted particle must lie in a single plane. For two particles cases, of course we have, this is true, because both velocities, they lie in a single line due to momentum conservation. For three particles, suppose that two particles lie in one plane and the third particle momentum do not belong this plane. It means that we have some part of momentum which not belong to this plane. It means that total momentum is not zero, which is not correct. So it means that all three vectors must belong to one plane. It means that A is not correct answer. B. Given a total kinetic energy of the system and the mass of each dotted particle, it is possible to determine the speed of each dotted particles. Let's see. For two particles, we have these two equations. We have total kinetic energy and we have zero momentum, and we have both masses. It means that we have two variables, v1 and v2, and two equations. So it means that that's correct. We can calculate what is speed of each particle. But consider three particles cases. Now we have one equation for energy and three equations for momentum, because it's vector form in 3D. But we have for each velocity we have 3 dimensions, so we have 9 dimensions for velocities and only 2 equations, so it's not solvable. It's no good. It means that B is correct answer. Let's examine C. Given the speeds of all but one dotted particle, it is possible to determine the speed of the remaining particle. It's not correct, because if we have speed of one particle and we don't know what are masses, so it means that we cannot use this momentum, zero momentum, to determine what is the speed of other particle. And same thing for three particles. Again, if we have a speed of one particle and speed of other particle and we don't have any masses, we cannot calculate third speed. And D, the total momentum of the dotted particles is zero. Of course, that's correct for a case of two particles and for three particles. So it means that it's not good answer. So good answer, remaining good answer is B. Problem number 22. A bullet of mass m1 strikes a pendulum of mass m2 suspended from a pivot by a string of length big L with the horizontal velocity v0. The collision is perfectly inelastic and the bullet sticks to the bob. Find the minimum velocity v0 such that the bob with the bullet inside completes a circular vertical loop. So first of all, we can draw the picture of this scenario. On this picture, first bullet stick this pendulum and getting a new velocity v1. After that, it starts to rotate till highest point, where it's getting speed v2, And the best way to do this problem is to probably to go backward. So first we have to find how much is minimum velocity v2 we can get here, not to fall down, because we have string, not a rod. So it means that it's not enough to have zero velocity here. This velocity must be such a way that there is no negative tension in this string. So critical value for this string is 0. So we can write equation for this motion on the top. So we have MA equal mg plus tension, where m is total mass of bulb and bullet. In a critical scenario, tension must be equal 0. It means that acceleration in the highest point is g. But we know that if body going by circular orbit, acceleration is centripetal acceleration, and we can calculate this acceleration by this way. So this is the connection between velocity in highest point and acceleration. So next step, if we know what is velocity in the highest point, we can find what is velocity in the lowest point right after collision. So we have to find what is velocity v1. For that we can use energy conservation. It means that kinetic energy in highest point plus potential energy compared to lowest point, that's equal to kinetic energy in the lowest point. So here we can use this expression substantiated here and find that v1 square equal 5gl. And the last step is to find what is initial velocity v0, because here we have absolutely inelastic collision. We have momentum conservation here, and we can write this equation. This is the equation for momentum conservation, and from here, using this expression for v1, we can find finally that v0 must be equal to this expression. So this is correct answer. v0 equal m1 plus m2 multiplied by a root from 5lg and everything divided by m1, which is E, correct answer. Problem number 23. Consider two uniform spherical planets of equal density but unequal radius. Which of the following quantities is the same for both planets? A. Escape velocity from the planet's surface. Let's see. First of all, we need to count what is mass of this planet using equation m equal volume multiplied by density. After that, we can find the force of gravity right on the surface of this planet. So this force equal this expression, where m small is mass of our object. From this formula we can find what is the acceleration of free fall right on the surface of this planet. As we can see, this acceleration proportional to radius for the same density. And after that we can find what is the escape velocity from the surface of planet using this equation. We know that escape velocity equal root 2gr. Or after this substantiation, we can take this formula. Here we see that escape velocity proportional to radius. So it means that it's not the same for both planets with different radii. Part B. The acceleration due to gravity at the planet's surface. We see that this is not true again, because this acceleration is proportional to radius. Let's check part C. The orbital period of a satellite in a circular orbit just above the planet's surface. We know that orbital speed right above the surface we can count using this formula, and the period we can find, that's a distance over speed, 2 pi r over speed. And we see that using this substantiation, we can find that this speed again proportional to radius. So radii are cancelled, and finally we have same period for any planet with the same density. So C is true. D. The orbital period of a satellite in a circular orbit at a given distance from the planet's center. This is not true, because each planet has a different mass, and on the same distance, if mass is higher, we have a higher orbital velocity. That's it. In this problem we have C correct answer. Problem number 24. A ball is launched upward from the ground at an initial vertical speed of v0 and begins bouncing vertically. Every time it rebounds, it loses a proportion of the magnitude of its velocity due to the inelastic nature of the collision, such that if the speed just before hitting the ground on a bounce is v, then the speed just after the bounce is rv, where r is less than 1, a constant. Calculate the total length of time that the ball remains bouncing, assuming that any time associated with the actual contact of the ball with the ground is negligible. So first of all, let's count what is the time for travel after the first plunge. That will be total change of velocity over g, which is 2v0 over g. After that, ball loses proportion r of its velocity, and now we have time for next travel is t1. We see that this t1 is r time less than t0. And the same thing happened after every rebound. So we have for each ti time, for number I rebound, we have time. So ti equal t0 multiplied by r power I. Now we can count what is total time, just summarizing all these times. So we have total time as the sum of all times. And finally we have geometric progression, and we can count what is the result for geometric progression, and this is the our answer. So, and the correct answer will be 2v0 over g multiplied by 1 over 1 minus r, which is a correct answer, A. Problem number 25. Two satellites are launched at a distance a from a planet of negligible radius. Both satellites are launched in the tangential direction. The first satellite launches correctly at speed v0 and enters a circular orbit. The second satellite, however, is launched at a speed of 1/2 v0. what is the minimum distance between the second satellite and the planet over the course of its orbit. So first let's draw the picture. So here we have first satellites going with a speed v0 by circular orbit radius a, and the second satellite going with a tangential speed v1 equal 1/2 v0 with a distance a from same distance a from this planet, but after that going to closest point at distance b from opposite side of this planet. So we have to count what is b compared to a. This problem looks like complicated if we do it straight away. So we can use energy conservation, momentum conservation, use all these equations, and finally can find the right result. But this is the long way. Definitely we have here a shortcut, and I can explain you this way. So first of all, how to count what is total energy for satellite on orbit. For circular orbit, that's a easy way. We can count it using formula potential energy plus kinetic energy. For circular orbit we have this expression. If this is potential energy negative, we have kinetic energy exactly equal half of potential energy, but with a positive sign, of course. And finally we have this expression, negative gmm over 2a, where a is a radius. But I can tell that this formula is good not only for circular orbits, but also for any elliptical orbit. If we take a as a half of a big semi-axis of ellipses, let's say like this, small ellipse, and we can use this knowledge. If this is energy for the first satellite, we can count what is total energy for second satellite. That will be this expression. We have potential energy in this point is the same, negative gmm over a, but kinetic energy 4 times less than kinetic energy of the first satellite, because speed is twice less. So finally we have this expression for total energy for the second satellite, which is negative g 7mm over 8a. This is from one hand, but from the other hand we know that this energy equal this expression. It's the same like this expression, but for elliptical orbit. And now we can just equalize this part and this part. Now after subtractions we have, and finally we can find that b just equal 1 over 7a, our original radius. So that's the answer E. Again, we used a special shortcut, and probably this is good way to solve such kind of problems, because there are not much time for big calculations.